We can think of the real numbers on a line, and with that, that means we can graph points, each number as a point on that line. So let's go ahead and try that out with 2 pi 5.3 and negative 5/9. So the real number line, hopefully you've seen this before. I'm just going to start with 0 in the middle because it's a good reference point. And then I'm going to go -1, -2, -3, -4. Of course, all of the portions between those are right there. They're graphed there. I'm just not going to write them. 2, 3, 4. In this case, I'm going to go a little bit further on this way. 5 and 6. So 2 on this real number line, it's just right here. So I'm going to show that by putting a point. And that is 2. Pi is just a little bit above 3. It's 3.14, and it continues indefinitely. Pi is just about here. That's pi. 5.3, just going to be a bit above 5, right around here. And -5/9, that's I think that's as a decimal 0.55555, and the negative of that. So it's just going to be just above the halfway point of -0.5. So it's going to be somewhere right around here. And so that's how you can graph numbers on the real number line in this one-dimensional thing. It's a line, so it's one dimension. Now, many times we want to write out a set that has an infinite number of elements that can't be listed. As we've talked about, the irrational numbers can't be listed, and therefore the real numbers can also not be listed. Now, the roster method, of course, won't work, but we can use set builder notation to describe what we're talking about. So the set of real numbers that's more than 4, but less than or equal to 7, is written in this way. The set of x such that x is between 4 and 7. It cannot equal 4, but it can equal 7. And of course, we're talking about x is the real numbers. Now, we can graph this set on the real number line. And the reason we want to do this is because it's just a bit faster to see what we're talking about. There's a nice visual representation of this set on the real number line, so let's use it. Open dots here are going to be not included, so open dots refer to less than or greater than. Closed dots will refer to less than or equal to, or greater than or equal to. Okay, let's go ahead and graph this. Let's draw a real number line. We have 4 and 7, so I'm going to only worry about those 2 points. 4 and 7. I'm not going to worry about writing 0 on there. 4 is not equal to it, so it's going to have an open dot. 7 is equal to, so a closed dot. And the set is everything that's more than 4, but less than or equal to 7. That's everything between these numbers, so I'm going to show that by drawing a line. So that's the set. That's the same exact set as this set builder notation. Okay, using this, we can actually do operations on these because these are just sets. So that means we can take unions, intersections, complements of these things. And the graphical representation is going to help us to do that. So for these first two, we have the same sets. I'm going to write the same, I'm going to draw it once and use it for both problems. Okay, key numbers, right? -2, 3, 5, and 10. So -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, the first set is 3 less than or equal to, so it's going to be a closed dot there. Between 3 and 10, not equal to 10, so I'm using open dot there. And draw a line between them. So that's the first set. The second set is -2 less than, so I'm just going to use an open dot. I'm going to draw it a little bit higher up, and then an open dot on 5 as well, and draw a line between them. Okay, the union says everything that's possible in the two sets. And so you can kind of think of these as Venn diagrams, but they're Venn diagrams in a different way. Venn diagrams, you use a circle, and a circle is two-dimensional. Here we're using lines, which are one-dimensional things. So you can kind of think of them as a Venn diagram like this. Like you can draw a circle like that, and then a circle like this, if you want. So you can see the overlap and everything. But I think the lines tend to be just clear enough the way they are. The union is everything possible from these two sets. So all of this stuff and all of this stuff here. So everything that's covered is going to be in the union. This stuff gets covered twice, but that's fine. That's like there being overlap, but you just don't repeat those things. Now 5 is included. 5 is not included in this first set, but it is down here in the second set. Wherever the line is solid, you include every number that's in that solid portion. So for instance, up here in this previous one, we had 5 and 6. 5 and 6 are both inside this previous set, as is 4.5, 5.5, 6.5, and every number between. So we're talking about every irrational and rational number between those, and there's infinitely many of them that's contained in this set. Okay, so the union is going to be the set. I'm going to write it as a set notation, or this set builder. All of the x such that I'm going to start on the leftmost side, because we always start with the lowest value first. -2 is not included, but it does start there. Okay, and it goes all the way up to 10. Everything between -2 and 10 are included. 5 was the only questionable point, but it is included in the second set, so we can include it in the union. We're not going to include 10 though. 10 is not included in either one. And of course, x is an element of the real numbers. So that's that yellow set there, the overlap of both of those two things. Now the intersection ends up being, I think, a little bit easier to see what we're talking about here. The intersection is the overlap of these two sets, just like it was for the Venn diagrams. We're only looking at the overlap, and the overlap is right here in this middle portion. Again, we care about what's in both sets. So 3 is in both sets. 3 is in this top set because there's a solid bar there. And 3 is in the bottom set because it's a closed dot. 5 is not in the top set. It is in the bottom set, but it has to be in both to be included in the intersection. Therefore, 5 is not included. Everything between 3 and 5, however, is included in the intersection. So it's going to be the set of all x such that 3 is the smallest value. It can equal 3, so it's less than or equal to 3. X, and 5 is the highest value. It is not equal to it though. Of course, x is an element of the real numbers. Okay, give this a try in number 5. All right, we want to simplify our the way we write these things, because these sets, though they seem like they're not particularly special, we use these sets all the time in mathematics. There's going to be this topic called domain and range, and these sets perfectly describe that idea. First off, we are always working in the real numbers. So this x element of r that I wrote here at the end, there's no reason to write it. We're always going to be working with the reals. If we're not, it's going to be specified that we're not. But you can always assume that we're working in the reals. So that's just not necessary to say x element of r. These sets are so frequent, like I said, that an even simpler way to write them is nicer. And that is called interval notation. So parentheses and brackets are used to designate the sets of real numbers. And all I've done here is I've removed the x element of r, right, that was there, because that's understood. That's always the case. And we're saying that 4 is this first number and 7 is the second. And as you can see, 4 is not included because it's not equal to here. And that has a parenthesis around it. So a parenthesis means the endpoint is excluded. And a bracket, the square bracket here, means the parenthesis, or sorry, the endpoint is included. So think of the parentheses like open dots and the brackets like closed dots. That's the key thing here. The reason why we don't use open and closed dots is because parentheses and brackets are much faster to type. There's a designated key on the keyboard to type it. So we are transitioned to this parenthesis and bracket to designate this information. Now, in general, I will use, when I'm graphing these things, I will use parentheses and brackets instead of open and closed dots, because the parentheses and brackets directly relate to the interval notation. And I'll show you that here. Of course, everything between the two endpoints, everything between 4 and 7 is included in our interval, just like it was for this previous way of writing it. Okay, let's go ahead and look at these interval notation. They're again just sets, and so we can do operations with them. Let me draw this one out. We have, let's see, 1, 2, 3, 4, 5, 6, and 7. Those are our key points. 4 to 7, I'm going to write this in, so if I were to write this how we have been, it'd be an open dot, line, closed dot. Open dot, however, is just a parenthesis. And a closed dot is a bracket. So that's how I'm going to write these from now on. It's clear for the interval notation, which is much faster to write. So that's where we are going to be going with this. Now, 1 to 6, these are both equal to, so they are both be closed dots. And in this case, they're going to both be brackets as well. And you can see we're talking about the union. So the union is everything between here. So all of this stuff and all of this stuff. We do include 4 because 4 is included in this bottom set. And we are going to include 1, and we are going to include 7. That's what gives us this set here. So I can rewrite this in interval notation quite simply by just writing the first set was 4 to 7, 7 included, union with 1 and 6 are both included in the second set, and this equals the set from 1 to 7. Much faster to write, lots of less things that we have to write out. Okay, this next one is the same idea, except now we're looking at the intersection. The intersection is the overlap. That's this middle portion here. So once again, we have 4 to 7 intersected now with 1 to 6. And that's going to equal 4 is not included because it's not included in the top one. And 6 is included because it's included in both. So we have 4 to 6. 4 would have an open dot, so it's going to use a parenthesis. 6 would have a closed dot, so it's going to be a bracket. Okay, let's move on. Here we have the set, let's see, -2 to 15, 23 to 77. We have, it can't equal -2 or 15, so it's going to be an open dots or parentheses. And then -23 is not included. 77 is included, so we're going to use a bracket. We're looking at the union. And the union between these two things is everything possible from the two sets. Now, previously, the union, I was able to rewrite the union as a single interval here because there was overlap. These two intervals do not overlap. Therefore, we cannot write this thing any simpler. And so this is actually the answer. We have to use the union symbol in it. But of course, interval notation is much faster to write. So we're going to write it using that. 23 to 77. And that is our answer. We have to have the union symbol in it in order to combine these two sets into one. Now, of course, we've been looking at all these sets we've looked at have always been like closed sets, like as in they've ended. They're from a certain number to another number. However, we can just keep going on up to infinity. And infinity is not a number. That's why you cannot divide by 0, because you'd think that would equal infinity, but it's not a number. It's more like a direction. And that is shown with these kinds of sets. So x, I'm just going to draw this here real quick. We have x less than 4, so 4 is here. X can't equal it, so I'm going to use a parenthesis. And it's less than 4, so I'm going to show that by just drawing an arrow. That's the idea of the direction of infinity. That means we go from 4 and allow everything below 4 all the way on down to negative infinity. All the negative numbers are included in this set. And we can write this as an interval. You always start the leftmost or the lowest value. The lowest value here would be negative infinity. So we're going to say negative infinity up to 4. 4, of course, has a parenthesis around it. And infinity is not a number, therefore can never be included in a set. So it will always, always have a parenthesis. Never put a bracket next to infinity. That's always wrong. It's always going to be a parenthesis. Okay, give the stuff I've talked about a try here in number 6. And let's actually do some kind of random interval operations. So for these first two, they are the same exact sets. So I'm just going to draw one and do both of them. We have 14 is up here, and then negative 1300 is down here. It's from negative infinity to 14, so it's going to be this stuff. And then negative 1300 is going to be a bracket on up to positive infinity. Okay, the intersection is quite simple. It's just the overlap. That's going to be everything between negative 1300 and 14. Negative 1300 is included in both sets. It's a bracket in the bottom one, and it's in that bar in the top one. So it's going to be included in the intersection. 14, however, is not included in this first interval. So it's going to have a parenthesis next to it. Okay, the union is everything that the either set overlaps. And you can see it's all of this stuff here from the first set, and then all of this stuff here from the second set. And you can see it covers everything. That is the lowest element is negative infinity. The highest is positive infinity. But this is just the whole real number line. Either one of these works. Interval notation says this is the way to write it, though. Okay, next one. We have negative 15. Let's see, negative 30 is the smallest value first. Then negative 20, negative 15. Just trying to kind of be somewhat accurate here. Negative 10, 0, 10, 20, 30 is somewhere up here. Okay, we have negative 15 to 30 and negative 30 to 20. Looking for the intersection is the overlap. It's of course a break here. That means these two sets are disjoint and there is no overlap. It's the empty set is the answer for this one. Okay, a couple more unique ones. This first one says, what's the union between -2 and 0? And then we also have these two things here. So let me do 0, -1, -2. So this first set is -2 to 0. And the second set is a set, not an interval, because of the curly braces there, which means it's the set of two elements, -1.53 and 0. So -1.53, that's just about here, and 0 is right here. So we're looking at the union. The union is everything possible. Well, -2 to 0 is all this stuff. And then we have this single point here and this single point here. Well, this single point is already included in the set. And this point includes 0 in the set now. So that means I can rewrite this in one go as -2 to 0, and now including 0 because it was included in the second set. So that's the union between those two things. For this next one, we have, let's do -1, 0, 1. -1 is right here. 0.5 is here. And 0 to 1 is this. So once again, we're looking at the union. We have this single point there, this single point there, and then this interval here. Of course, this point's already contained in the interval. This point, however, is not, so we have to include it. However, this is completely separated. There's a disjoint between the -1 and this interval here. So we have to write it using a union. And since it's a single element, I'm going to use it as a set. This set of -1 unioned with 0 to 1. And that's our answer. We have to use the union again because there's a disjoint between these two sets. But since we're unioning them together, they are one entity. It's just a weirder way of writing it with the interval notation. Okay, give these ideas a try in number 7 and 8.